want to move on to a situation where we have multiple reactors in series. So looking back, picking up with the problem that we were doing on Monday, I'm basically using the exact same conditions. So we have a 500 cubic meter reactor. We're starting with clean water. So C naught is equal to 0. At T0, we turn the pump on and we start pumping a solution. We have a reactive substance with a concentration of 100 milligrams per liter. The flow rate is 50 cubic meters per day. The volume of solution in the reactor is constant, so V is constant. And the substance degrades according to first order kinetics with a constant of 0.25 inverse days. Now, we showed that when we had one reactor with 500 cubic meters, the concentration leaving that reactor, we have Cn is equal to 100 milligrams per liter. Because we have a reactive substance, the concentration leaving the reactor is 28.6 milligrams per liter. Now, the volume here is 500 cubic meters. Question is, what if instead we have the situation, we still have Cn is equal to 100 milligrams per liter, but we have two reactors in series. So we have reactor here, 215 cubic meters. We have a second reactor, 250 cubic meters. So the total reactor volume is the same. The question is, what is the concentration leaving? So I just drew it. I'm going to skip this slide. Okay, so let's just look at the situation where we have a CSTR. So we're again looking at a CSTR. We have a series in series with first order decay. Okay. So in the case of the situation we have, each of these is 250 cubic meters, and we said for the problem we're looking at, the initial concentration is 100 milligrams per liter. So we can write two mass balance. Okay. C1 is 100 milligrams per liter. Qn is 50 cubic meters per day. C2 is C out from reactor 1. Volume is constant, so C out is the same. K, we said, was 0.25 inverse days. C2 is C out from reactor 1, and the volume here is 250 cubic meters. So it's the volume of reactor 1. Okay. C2 here, notice, C2 here is what the concentration leaving reactor 1, and that's the same concentration entering reactor 2. We're assuming that there's no reaction in that piping between reactors 1 and 2. Qn is still the same. Okay. C3 is C out from reactor 2, and V2 is 250 cubic meters per day. Okay. Now we're only going to look at the steady state concentration. As I mentioned, most of our reactors in water and wastewater systems will operate at steady state. So I've described these to us. Okay. So we have, as I mentioned, Q is constant, which means the volume is constant. Okay. At steady state, we can say that this, so we've pulled this out, V dc dt, and that equals 0. So if we have steady state conditions, the change in mass with respect to time is equal to 0. And if we substitute in for these equations, and we'll solve for C2, so it's algebra, C2 is equal to 44.2 milligrams per liter. And I'll write this one, okay? So C2 is 44.2 milligrams per liter. Q is 50 cubic meters per day. C3 is what we're looking for. Q is the same. And V was 250 cubic meters per day. And that equals 0. And notice here, I have units. I haven't converted. I could convert in 1,000 liters per cubic meter. I could convert it, but I'm going to have 1,000 liters per cubic meter in every product, so it cancels out. And C3 is equal to 19.75 milligrams per liter. So significantly less. If we go back and we think about the reactor before, we started out at 100, and when we had a reaction with one reactor, we had about 28.6 milligrams per liter. When we have two reactors, so the total volume is the same, we have a lower concentration. So two reactors, same volume, two reactors is more efficient in terms of achieving a lower concentration than that one reactor. Now, we mentioned the other day that detention time is equal to the volume divided by the Q. So we can substitute so that we have detention time in the equation. Okay, so this is the same set of equations where we have two reactors in series. And so C2, again, is the concentration leaving reactor 1, and it's also the concentration entering reactor 2. So it's important to recognize that. If we have steady state, this is equal to 0. And what we end up with is this equation right here, okay, that says that the concentration leaving the nth reactor is equal to the concentration entering divided by 1 plus K times the detention time in each reactor, the sum to the nth power. So we had 4 reactors, each one 125 meters cubed. Each one 125 meters cubed, same detention, same rate constant. So this is equal to, so C to the fourth reactor is equal to 100 milligrams per liter, 1 plus 0.25 inverse days times 125 meters cubed, its whole sum to the fourth. So what if we have 10 reactors, 100 milligrams per liter entering, 1 plus 0.25 inverse days, first order kinetics. We have 10 reactors, so the total volume equals 500. We'll keep this constant. So the volume of each reactor is 50. Take this to the 10th. So the concentration, I'll just write that 10.7. So it's 10.7 milligrams per liter. So we had, with one reactor, it was 28.57. With 2 reactors, it was 19.8 milligrams per liter. And with 10 reactors, it's 10.7 milligrams per liter. And the question was, did I put in volume for detention time? And you are absolutely right. I did. Did I do that all the way through? Thank you for catching that. This should be the detention time. Okay. That should be detention. So what was our flow rate? Is 50 cubic meters per day. Our volume for each reactor is 50 cubic meters. So our detention time is 50 cubic meters divided by the flow rate, and it's 1 day. So this here, and this here is 1 day. Thank you for mentioning that. And I apologize for the error. Makes more sense?
So were all the calculations though, were they done with 1 day then for that?
So let's go back here. Let's go. Okay. So here, notice, and okay. So in this case here, notice I have volume. Okay. I haven't written it in the more general form. So in this case, it's volume. So then when I substitute in here, I have, so this was C2 times the flow rate minus C3 times the flow rate minus K times C3, that's C out, times KCV, times the volume. So in this case, it's volume. Okay. Here, when we go to, sorry, this equation here, which here detention time has been substituted for V over Q. So it's basically just a division. So we have dC dt, volume here, equals Q in Cn minus Q out C out minus KC V. If I divide both sides of the equation by V here, then the V cancels, and I end up with Q over V, which is the inverse of detention time. So I can write it here as Cn minus C out, because I can factor that out. V over Q is detention times divided by the detention time minus Kc. So that becomes the general equation. Okay. So from that equation here, we get this equation right here. So at steady state, C, whatever this would be, C4, okay, is simply equal to concentration divided by 1 plus K times my detention time, the sum to the n power. Okay, so it was correct before, where I used volume before was correct. What I did wrong here was right here, okay, and I'm going to leave it this way. This is detention time. So let's calculate the detention time. We have 50 cubic meters per day, 125 meters cubed, and that's my detention time. That goes in here. So that was wrong here. I apologize. Any questions about this equation here? Because I know you've got a homework problem, and I apologize for making that mistake. But hopefully we've clarified it now. So this was wrong. This is detention time here.